Okay, so this is our last section in Chapter 6, or pipe flow, and we are going to talk about what are called minor losses. So we've already done frictional losses, and we had an equation for our HF. We're going to have other losses just because any kind of disturbance in the flow caused by diameter changes, elbows, tees, orifice, throttle, valves, inlets, exits, they're going to cause some kind of flow disturbances. For example, if you have, say, a sudden expansion, so here you have a velocity profile, maybe something like that, upstream, and eventually downstream it looks kind of the same, only with the bigger diameter. But in between, you're going to have some strange stuff going on because the flow has inertia, so it's not going to be able to make these turns. And so it's going to do something like this. And in these kind of void areas, you're going to get separation. Okay, and separation is going to just be lost energy. And so that means that, your pump or whatever is being used to drive this flow through this sudden expansion is going to have to work a little bit harder in order to get the same flow rate as it would without this sudden expansion. Okay, so the pump would have to overcome both the frictional losses and these minor losses. Okay, so how do we take this into account? Well, we're going to use something called HM, which is kind of like our frictional head losses, and it's going to be P1 over rho g plus V1 squared over 2g when we do our energy equation, plus Z1 equals P2 over rho g plus V2 squared over 2g plus Z2 plus plus we're going to have our HFs, but if we have something like this where we have an expansion, we're going to get one HF for this section, and we're going to get a different HF for this section, right? Because they have different diameters, there's going to be less frictional losses in this bigger diameter section than there are in that section. So we're going to have to put in a summation sign here. So for all our pipes in series, each pipe is going to have its own frictional head loss, and you can just sum those. Also then, we can have multiple fittings, so we need a summation there, and those fittings, valves, whatever, inlets, exits, and so forth, each one will have its own K value, and so it'll have its own minor loss value. And you have to just sum them up on a path from one place to another, from your inlet to your exit. All right, so the equation for minor losses. It's kind of like what we had for frictional losses, but now it has this K value in it. Okay, so K V squared over 2G is the equation for minor losses. It's on your equation sheet. And the K is what you get, a different number for a valve than you do for an elbow, and so forth. One thing to remember when you're calculating this HM is you've got a V in here, and if you have something like an expansion or a contraction, you have multiple V's involved. Okay, so here, for example, this is a contraction. You have a V1 and a V2. What you need to do in your HM calculation is use the largest of the velocities. Okay, so for this contraction then, the HM would be K, whatever value you get for a contraction, times V1 squared over 2G. Okay. So getting the K values, that's what you have to do in order to solve these problems. Find the K values. Now normally what you would do is go to the manufacturer and figure out K values from them, or measure it yourself, because what we're going to get in the book is not very accurate, but you're going to have to use something for your tests and for your homeworks and so forth. So we're going to just use these tables and so forth in our books. Okay, so let's start with valves. How do you find the K values for valves? We have a couple different places. First you got to know what the valves look like. So this one is called a gate valve, and this is kind of a side view. If you looked at it from this direction, it would look like a disc. This one is an angle valve. This one is a globe valve. Okay, so globe valves are the highest losses of any of these. And if you look at this, even as it's open, the flow has to go here, 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 like that in order to get through. So there's a lot of losses going on in there. You're going to have little separated areas all over the place. This one is a check valve, a swing check valve to be specific. And here is a disc type gate valve. Okay. Okay, so the thing about valves that make them a little bit more complicated than some of the other fittings is that they could be fully opened or they could be partially opened. Okay, so partially open, you have to make adjustments. Okay, so table 6.5 gives you some values for valves. If you are using table 6.5, it only gives you open valves. Okay, so what you can do then is use this little chart here to make adjustments if it's partially opened. Figure 618B gives you some more valves, and it gives it to you already with a x-axis is how far open it is. So you could just read the values off of that. And the same thing for figure 619. Those are for butterfly valves, which are similar to the really kind of similar to the swing check valves. So if they're not fully open, what you're going to do is either use table 6.5 and then look at these as multipliers here, depending on how far closed they are. So if you had, for example, a 1/2 inch fully open globe valve, if you're looking in table 6.5, you're going to get a K value of 14 for a 1/2 inch pipe, fully open globe valve. Okay, so that's really high. It probably in real life isn't that high. But then if you take that number and you say, okay, it's only 25% open or else 75% closed, you're going to multiply it by some factor between 6 and 8. Well, let's try 7. So then our K value would equal 14 times 7, which is 98, which is huge. But there are going to be a lot of losses through that. If you use figure 6.18b, you're going to just read off there 25% open. It's the very beginning of the graph. It looks like K is about 15. Probably a little bit more reasonable, but still. Big difference, okay? So you don't want to really trust these values if you're really in real life doing some of these problems. Okay, so that's valves. You want to either use table 6.5 or want figures 618b or figure 619 to figure out what your K values are. And if you have a choice, then either one will be right. I'm not going to count you wrong for picking one over the other. Another thing is elbows. Elbows are going to give you some losses. Flanged elbow is better than screwed elbow. This is a flanged elbow, and it's going to just connect to another piece of pipe that's flanged as well, and it's going to go like this, and maybe you put a bolt through here. Okay, very little disturbance in the flow, at least at the connections. So flanged is better than screwed. Screw is where one side screws into the other side. So you need to know which is which before you decide to pick what K value you're going to use. Okay. In all of these, in addition to the minor losses, there's going to be frictional losses through here. So you include the total length of the elbow in your HF calculation because that has an L in it as well. Okay. So a couple things to remember, just try to find your K values off these graphs and tables. Use the largest velocity in your HM calculation and use the total length, including that through your elbows or valves or whatever in your HF calculation. Pipe bends, similar to elbows, but usually not quite as bad. There's another figure for that. Basically just look it up. It's based on the radius of the turn over the diameter of the pipe. When you go around these bends, again, the inertia is going to cause some separation, and you're going to get some circulation in this direction in the bend here. Okay, so you're going to get losses due to that. Okay, usually not as bad as elbows, though elbows are usually sharper. And again, you want to include the length of the bend in your HF calculation. Inlets, be careful. It's easy to forget about the inlets. But inlets also will cause some losses. Best inlet is these rounded inlets. Worst would be these re-entrant inlets. Oops, not worst. Figure 621 has loss coefficients for those. So, just get used to looking those up. It's not too hard. Exits. If it's exiting into air, then just use K = 0. In other words, ignore it. Okay, but if it's a submerged exit, and submerged means, so maybe you have some sort of situation with a turbine or something, and it comes down into a lake, and here's your free surface or a tank or something down here. This is a submerged exit. Okay, there's your submerged exit. Okay, whereas into air, if it's just shooting off into air, and K is 0. If it is a submerged exit, just use K = 1. Okay, you don't have to look that up in a table. Just use K = 1. Expansions and contractions, another figure. So there's a whole bunch of figures, and again, I'm going to give you these on the test. Expansions much worse than contractions, and again, use the highest velocity in your HM calculation. Gradual expansions and contractions, those are nozzles and diffusers. There's also just more graphs and more tables. It's just a matter of getting used to looking those up on the tables and graphs. And again, like if you have two different places to look them up, you see how much different they are, just like what we did here looking up the globe valves. We got 15 or 98. That's a huge difference. So if you were doing this in real life, you would not use the books, tables in the books. You would use something else, probably from the manufacturer. You also need to take into account if the pipes are old, there could be buildup in the pipes. So for instance, you see this guy peering out through one of these big pipes. Look at all that crud that has built up. It's kind of like it builds up in your arteries. The losses through this crud is going to be much higher than the losses through this clean pipe. So you need to keep that in account. And again, doing your own experiments, that's the best way. So let's do an example with minor losses. So just like all our previous pipe flow problems, we're going to be using the energy equation for this. So let's just start by writing down the energy equation. And that is P1 over rho g plus V1 squared over 2g plus Z1 equals P2 over rho g plus V2 squared over 2g plus Z2 plus sum of our HFs plus sum of our HMs plus HS. All right, next thing, let's go ahead and pick a coordinate system and pick an inlet and an exit, so a lot of our terms will cancel out. And so if we look up here at the problem, you want to see if there are any free surfaces, because that is the best place to put an inlet or exit. Okay, in this case our flow is going this way, so let's put an inlet here. And next best place to put an inlet or exit is where we have going out into the atmosphere here. So we want our exit to be right where this pipe exits into the atmosphere. And when we do that, then we're going to be able to use P2 is 0, just using gauge pressure. Okay, so when we have the free surface, remember, P1 is 0, V1 is 0 as well. Here at the exit, P2 is 0 as well. We can't say that about V. We do have a V going out there at 2. Then let's look at our Z's. We need to put in a coordinate system so we can do our Z's. I'm just going to put my Z equals 0 down here at 2. And that's going to make Z2 is 0. And the reason I did that was so I'd just get a positive Z1, which is going to be 50 meters. Okay, and what we're trying to find now is turbine output. So we're going to be solving for HS. And at this point, we've canceled out everything we can cancel out. If you look at this problem, even though the diagram looks like the pipe diameters change. There's nothing really to indicate any expansion or contraction, so the diameter of the pipe does not change throughout this problem. So we really are only going to have one HF, but we're going to have multiple HMs. So I'm not going to go through how to calculate HF. It's just going to be HF. Oops. HF is our usual F V squared L over 2dg, and we can calculate Reynolds number, about 100,000. Okay, and from that we can get our F, well, that plus our epsilon over D for cast iron, and we get F is about 0.031 from Newty. All right, and with all that, we can just plug in and you get HF equals 15.9 meters. Ooh, 15.9 meters. I skipped too many steps here because in order to get that, I need V. And so let's just erase that and put in V equals Q over A. And be careful, if you have different pipes, V is going to be changed. Different pipe diameters, V is going to change. In this case, throughout this whole area where we're going to have frictional head losses, we have a constant V because we had a constant D. Okay, and it is just going to be Q over the area using this diameter of 5 centimeters. Okay, and if I do that, I am going to get V2 equals the V that we're going to use in here. For our HF, and that comes out to 2.04 meters per second. Okay, so with all that, we're going to get HF equals 15.9 meters. Okay, so basically we have a turbine here, and we have 50 meters, 40 here plus 10 meters of an elevation change, which means we have 50 meters of head available to our turbine as in the form of potential energy. And what we want to do in a turbine is get the most energy we can out of that turbine. So unfortunately, though, the frictional head losses are going to suck up 15.9 of those available 50 meters right away. Okay, so that's our HF. Now let's go back and we're going to have to figure out our HMs. Okay, so our HMs are going to be based on all of the fittings, entrance, exits, valves, whatever. You don't count the turbine as having one. That all goes into the HS. All right, so if we look at this, what I usually do is label all of my different fittings. Look carefully at this. And easy one to forget is the entrance. We have an entrance here. So that's going to be A. Here's B. It's going to be my next fitting. It's a screwed elbow. C is a valve here. D is another elbow. And then you got to look at the exit sometimes. If it's exiting into the air, you can ignore it. If this was exiting into another tank, though, we would have to include it, and it would have a K value of 1. All right, but we don't have to include it because it is exiting into the air. All right, so let's figure out then what are our HMs, or some of our HMs. And HM for each different fitting is K V squared over 2G. All right. If you look at this, anytime you had an entrance or an expansion or contraction, you need to figure out which V to use. And you want to use the largest V. In this case, our largest V, the only place we have a velocity that's changing is at the entrance. And the largest V is the V that's going through all the other fittings. So we're going to have all the same V's in this case. For this problem. Okay, which means we can factor that out, and it's going to just make our life a little simpler. We can say the sum of HM equals our V squared over 2G, because that's not changing, times the sum of our K's. All right, so let's find all our K's, and that's just a matter of looking up in tables or graphs and figuring it out. And sometimes you have options, like those elbows are going to give you options, or the valve. Which one do I want to pick from? Well, if you're trying to be super conservative, you probably want to pick the bigger K values, I'm not going to try to be super conservative here. I'm going to pick some of the newer K values from the graphs instead. But first of all, let's start with the entrance. That's A. And if I look in the book at figure 621, and you could pause the video and pull out your book if you don't have it out, that might be useful. Because if you look at figure 621, there's a graph, and it looks, it's got a bunch of lines here for different types of entrances. If you look right there, there's a little thing that says sharp-edged, and that's what we have. Happens to be at about K is about equal to 0.5. All right, so there's our K value for our entrance. B is an elbow, and D is the same elbow, so we can just do two of those. You're going to get K is about equal to 0.28, and that's if you look in figure 618A at a Reynolds number of about 0.1 million. Okay, your other option there would be to look up on table 6.5, and you're going to get much bigger numbers. So like I said, this is not the conservative estimate. C is a half-open globe valve, and again I have options on this one. I could use table 6.5. If I do that, I need to adjust it by the previous pages of the notes. It had an adjustment factor that I could adjust it for a half open. Or I can use figure, and this is what I did, figure 618B. And looking at half open, it's going to just give me a K value of about 6. Okay, this is way off from what you would get using that other method, so just keep that in mind. So some of our HMs then are going to be, some of our HMs are going to be about V squared over 2G times 0.5, plus we had 2 elbows for the 0.28, and these are non-dimensional, these K values, plus 6, and that's going to come out to 1.5 meters. Back to the energy equation then. We've got everything we need. We're solving for HS. We're going to have here 50 meters on the left side equals our V squared, 2.04 meters per second squared over 2G. That's our V2 over 2G term, 9.81 meters per second squared, plus the 15.9 meters for our HF, plus the 1.5 meters for our HM, plus HS. And solving that, you get HS equals 32.4 meters. All right. What we're looking for was the turbine power. So that HS equals W dot S over M dot G, which again equals W dot S over gamma Q. Okay. And so what we're going to get, is W dot S, and remember W dot S that we're calculating from the energy equation is what we're going to get from the fluid. And that comes out to be 1270 watts. Okay. W dot that we actually get from the turbine, if it's 90% efficient, is going to be 0.9 times W dot S, which comes out to be 1140 watts. Okay. So that's how you do it. The minor losses is just a matter of being able to look things up in tables and graphs in order to plug them in. Notice that out of the 50 meters available, we only got 32.4 meters in the end to our turbine. The rest were lost as frictional and minor losses. All right, so neglecting the minor losses, we would have gotten more power out, so that would have definitely not been conservative. That wouldn't have been good. It would only be off by 5% error. Neglecting all the losses would give us a 50% error though, and losses did consume a bunch of our available potential energy. So that's it. Go ahead and finish your quiz. I'll see you later in class.